Thank you very much. Thank you everyone for coming and hearing some, I think, very diverse and creative different forms of astronomy. I'm not going to say any beautiful poems like Miguel just did. I'm going to try to do some straight astronomy, but bear with me and you might learn something too. So today is, I'm going to be talking about something I've been working on for a couple decades since I was a grad student. That was on a new class of objects called brown dwarfs. I say new, but I think after 20 years they're probably not new anymore. But all right. And these are things that I'm going to convince you are invisible stars, which sounds really crazy and is true. I'll start by just showing just a beautiful, typical picture of the night sky. If you get out to a dark spot on a clear night, you can see things like the Milky Way, but you also can notice that the stars have different brightnesses and also different colors, right? There are different kinds of stars out there. And a good demonstration of this, this is an animation. This is a picture of the Omega Centauri Nebula up on the, Galbraith cluster up on the upper left. This is an old cluster full of lots and lots of stars, like 10,000 stars in this cluster. And this is a Hubble Space Telescope image of just one part of that. I'm going to play a little video here where we're going to organize the stars by their colors first. So we're going to put all the red stars off to the right and all the blue stars off to the left. And then we're going to organize them according to their brightness. So all the bright stars go to the top and all the faint stars go to the bottom. And those of you who have taken Astronomy 101 will already know, wow, amazing pattern appears, right? This pattern of the Hubble, the HR diagram or the color magnitude diagram, depending who you can talk to. All right, this pattern of all the different kinds of stars out there. I guess we're going to see it twice, but we're going to go past here. All right, so that pattern is mapping the different kinds of stars that are out there, and that pattern is mostly due to the different masses of stars. Right? If you look at kind of the main part of that sequence there, they kind of follow the sequence from really big, bright blue stars, which we classify as O stars. And maybe as of the questions, I can get to why we have this random set of letters for this. All right, but really big bright stars off to the right over here, and really faint stars off to the left. And this range is from about 10% the mass of the sun up to maybe up to 40 times or so. And our sun is one of these G stars there. All right, so lots of different kinds of stars. Now, to understand why these stars have these different properties, it's useful to remember how stars form in the first place. And they start in these massive globular clusters. So this is a picture of one of our most famous molecular clouds that are out there. This is the tip of the Eagle Nebula. And each of those little kind of pixie horns that are coming off there is going to form a star. And that star is just that collapse of all that gas. And as that star collapses down, gravity takes over. And as it falls, energy is transformed from gravity into something else. Now, in that case, it was the sound of my shoe hitting the floor. In the case inside the star, that gravitational energy is turned into heat energy. And that heat energy makes it hot enough to start fusion reactions, which is the stuff that gives us everything besides hydrogen in the elemental table. And then once that kicks in, you have a nice, happy, stable star, happily fusing hydrogen, shining up in the sky, of course, until it blows up and dies. Look, I don't make the rules. It's just what happens, right? But the key point is that it has to get hot enough to start those fusion reactions. You don't have a happy, stable star unless you have fusion. And that's, in fact, why we have these different types of stars. The really big, massive stars can start those fusion reactions right away, and they go through those fusion reactions much faster, so they live a very short time from an astronomical perspective, only about 3 million years. Whereas the slow and steady stars to the right side can last for hundreds of billion years to trillions of years, very slowly burning its hydrogen store. All right. Now, so we already did our trivia question. I got one more trivia question for you. Of all of those kinds of stars, which one do you think is the most common in our galaxy? All right. Let's take a quick vote. Who thinks the O stars are the most common stars in the universe? Okay. All right. Who thinks the G stars, the sun-like stars, are the most common stars in the universe? Hands are like this high. Or, yeah. Who thinks the M stars are the most common stars in the universe? All right. And who thinks all the stars are exactly the same number, doesn't matter at all? Awesome. Okay. Good. Most of you are right. These guys, these little inky-dinky stars, pathetically small and red, make up 70% of the stars in the galaxy. 70%. All right? So forget the world. The meek shall inherit the universe, right? All of these tiny little stars are what makes up the universe. So you can ask the question, if there's so many stars in this little type of star, how small can we make them, right? So if there's like 70% in this like tiny thing, can we go to like half the size and make up like 170%? No, but you know, we'll work on the math, right? How small can we make these things? Well, it turns out that there's a limit, and that limit was discovered in the 1960s. And that limit is because of something called quantum degeneracy. And this is a theory that several early scientists in the early 20th century devised to explain sort of the inner workings of matter at the very fundamental scales. And one of the sort of principles that came out of this is known as the Pauli exclusion principle. Can be stated as no two identical fermions, particles with half-integer spin, may occupy the same quantum state simultaneously. Everyone got that? Yeah. There will be a test at the end. All right, if that's not clear, here's another way you can say it. You can't put two things in the same place at the same time. There's actually a better analogy that we like in California, where we love our cars, but we don't have enough parking. This is called the parking degeneracy problem. All right? So in a normal parking lot on like a Sunday morning, right, plenty of parking spaces, you drive in, you just park, no problem, right? You get down to like the middle of the day, no parking spots. People are driving like crazy because they got to rush to that one open spot. All right, a lot of jittering around, a lot of energy, right? That is degeneracy with cars, okay? So it turns out inside stars, not cars, you can have degeneracy from electrons, the smallest little particles, and that turns out to provide a pressure support that stops stars from collapsing when they get dense enough. And that pressure support turns out to stop the formation of stars at about 7% of the mass of the sun. Now, I should be very clear here. Stop the formation of stars doesn't mean that they don't form. It's just they don't get hot enough to start fusion. They could still form in the sense of a bunch of gas gets together and collapses down to something that's 7% of the mass of the sun or less, but it doesn't fuse hydrogen. It turns out that size is about the size of Jupiter, too. All right, so it's a pretty small object from an astronomical perspective, but these are things that don't fuse hydrogen. Now, you would think that, okay, that seems pretty cool. Okay, I thought it was pretty cool when I started my thesis, right? But maybe it's cool, all right? But what do these things actually exist? I mean, they thought about this in the 60s, so maybe we go out and look for them. So people started looking for brown dwarfs starting in the 60s. In the 60s, they found none. And then in the 1970s, they found none. And in the 1980s, they found one, but it turned out to be like a little futz thing on the image. So there's actually none. All right. So think of the astronomers at the time. Theory says, oh, we should find all these like really tiny, cool little faint things all over the place. There's lots of them and stuff like that. Nothing, not a thing. All right. So you can imagine, like, you know, people are starting to think about their careers at this point. The problem is if you don't have fusion reactions happening in your core, you don't have that source of energy to keep hot enough to shine out in the sky. And so these brown dwarfs, one of their interesting properties is that they actually cool over time. And we'll talk about a little bit later how cool they actually get. But cold things actually emit their light at other wavelengths. So here's our electromagnetic spectrum, all right? The wave in the middle there compared to some sort of regular size things for comparison. And you can see here the sort of very narrow part of the electromagnetic spectrum that we can see with our eyes, the visible band. But there's a lot of the electromagnetic spectrum that we can't see with our eyes. And then back in the 1960s and 70s, we also couldn't see with the instruments that we had available, which are mostly photographic plates and increasingly then CCDs. These are all detectors that can measure the visible light. It turns out that, in fact, if you want to go to lower energy things, cooler temperature things, you have to move to longer wavelengths. So you have to move over to the infrared part of the spectrum, right next to the visible. And to understand why, another analogy I like to think of in California, we love to go to the beach, and there's two great sources of energy at the beach, the sun and a fire. All right? Now, for the sun, all right, the surface of the sun is about 5,500 degrees Celsius, about 10,000 degrees Fahrenheit. And, you know, you like can sit there, it's nice and warm, but you probably wouldn't want to stare at it. That's my advice to you at the end of this talk. Don't stare at the sun. Okay? All right, so this is something that's more bright than hot, right? It's going to blind you, but it's not necessarily going to burn you unless you stay out for a long time. So it's brighter in the visible than is the infrared. Well, that campfire, which can have a temperature about 300 degrees Celsius or so, about 600 degrees Fahrenheit, All right, you can stare at that fire all night long, especially if you're stoned, all right? And nothing's gonna happen to your eyeballs, right? You're just gonna trip out, right? But get too close and you're gonna get burned. So this is something that's more hot than bright, or another way to put it is more infrared radiation than visible, all right? So temperature tells you how part of how much light is coming in different bands. So it required astronomers to develop infrared detector technology. Let me take that back. It required the military to develop infrared detector technology, and the astronomers to steal that technology and to actually do something good with it, all right? So we developed these detectors. We as a community developed these detectors. I should say the thing on the left there is a detector that we used for the first instrument I ever built. And that detector cost about $500,000, which was more than the mortgage of my house, which is really frightening to hold, just say. All right, and we put in these big machines that we cool down, and then you get a completely different view of the universe. So here is a picture, a familiar picture of the Orion, region around the Orion constellation on the left side. And on the right is the same picture, but out in the infrared. You can kind of see Orion is there, but there's this other thing here. And that other thing is actually part of the cloud and material that's forming stars in the Orion region. You can only see it out there in the infrared, can't see it on the visible at all. Right? So you see completely new things. Here's a picture of Messier 81, a spiral galaxy. On the upper upper left there is a picture you'd see in a very deep visible band image. When you look at the infrared, all of a sudden all these little hot spots pop up. All those hot spots are all the star-forming regions in these galaxies. So by looking at the universe in different wavelengths, we actually see different things. We learn different things about the universe. If we can look at people, we can see different things about people. All right, so there's people. All right, very hot here. So eyeglasses, not so much. All right, here's what animals look like in the infrared. Yeah. Yeah. Giraffes have spots even in the infrared. That's pretty cool. All right, and then here is, I'm going to show you what a brown dwarf looks like in the infrared. So here is an image of the sky around one of the brown dwarfs that I studied when I was a grad student. This is a visible light image, and it's inverted so all the stars are black and the background's white. It's just easier to see stars in that kind of frame. So that's the visible light image. Here is the infrared light image. Where's the brown dwarf? Okay, I'll do it again. Here's the visible band image. And here's the infrared image. Okay, so Daniel's telling me to go back and forth, so I'm going to go back and forth really quickly. And then sometimes you get lucky and the universe just throws a big circle right around the thing you're looking for. That's the infrared image, and there's the visible image. Gone, right? That's an invisible star. Whoa! I know! That's amazing! All right, so again, we needed these new ways of looking at the sky to find this population of stars that we predicted 30, 40 years ago and now can finally see for the first time. And now we have like thousands of these things. They're actually kind of boring at this point, which is kind of sad for my career, but that's all right. But it turns out these objects are so common that they turn out to be some of our nearest neighbors. So this is a graphic from NASA showing all the star systems that we know today within about 6 light years. And 6 light years sounds like a really big distance, but from kind of a galactic where stars are, it's actually pretty small. These are our nearest neighbors. And you can see Alpha Centauri kind of on the left there, and Proxima Centauri, that system that Alpha Centauri, of course, we could see with our eyes. So they're not just, you can't really say when it was discovered, but we know when the distance was measured. Proxima Centauri was discovered about 1917, and then Barnard star, which is a very fast-moving star, very cool star, was discovered about the same year. So those stars were discovered over 100 years ago. In the last 5 years, we've discovered these other systems that are also in the same sort of region. So WISE 0855, WISE 1049, and WISE 0720. Now, if you're looking at WISE 0720 and getting very nervous, because that looks really close, all right? That's where it was about 70,000 years ago. Today, it's about 6 parsecs away. It's much further away. But we know it was that close because right now it's moving almost exactly away from us in a radial direction. So we can back up where it was 70,000 years ago, and we find out that it was actually so close to the sun it probably passed through the Oort cloud of our solar system, which means it could have perturbed some of the comets in that solar system, which means in about 2 million years we might get in some trouble. So start planning now, all right? 2 million years. 2 million years you got. Now, if we go back in time and we say, well, what did our ancestors see up in the sky when that star was passing by, well, they would have seen something like this. This is 70, so here's our time, 70,000 years ago, all right, on November 3rd. At 11:20 in San Diego, all right, toward the south, and you can see Rigel and Arknar there, and this star was kind of up in the top there. You can't see it, all right? It's invisible. Even this star, even though it was one of the closest things to the sun, would still have been invisible because it's so faint at optical wavelengths. If you had infrared eyes, it'd be one of the brightest stars in the sky, all right? But in the optical, no one would have even noticed it. Right, so that's the most amazing thing about these stars. They literally are invisible even when they're right up against the sun. We still can't see them. Now here's some other interesting things, because if that star passed so close, maybe there are these cool brown dwarfs around. Maybe there's one even orbiting the sun. All right, this is not the sun, but this is a sun-like star with about the same age as the sun. It also has a planet around it, and probably has more than one planet. And it turns out it has a brown dwarf orbiting it at about 15,000-year orbit. And again, if there's a terrestrial planet around the sun, they can't see this brown dwarf. It's too faint, right? It's still invisible to their eyes, right? So people are actively looking to see, we know most stars in the universe have other companions around them, other sort of pair stars. The sun, so far, it doesn't. So people are still looking to see maybe there is one, but it's a brown dwarf. Brown dwarfs, also, I told you how they collapse down to these very dense states. In fact, they are the densest hydrogen gas regions in the entire universe. If you can crack open a brown dwarf like an egg, you would find that the inside has a density of about 1,000 grams per cubic centimeter. For those of you who don't memorize your grams per cubic centimeter scales, water is 1, lead is 11. That's 1,000, all right? That's really dense. In fact, so dense we can't even produce those kind of environments on any lab experiments here on Earth. And so we don't know what the state of hydrogen is in those stars. Is it metallic? Is it crystalline? Is it something else? We don't know, right? So those are that's a cool thing about brown dwarfs. The other thing that's cool about brown dwarfs is they're cool, all right? Really cool in terms of temperature. I said that they don't have fusion, so they cool off over time. And if you wait long enough, you can get objects that are incredibly cold. So this is WISO 855. This is one of the nearby brown dwarfs. It's the closest Y-type brown dwarf. That's another letter for the spectral sequence. And the graphic shown here is how we discovered it. It's actually moving. It's so close that you can actually see it moving across the sky if you take images over the course of a few years. And when we measure the temperature of the star, it's about minus 25 degrees Celsius. Yeah, it's not minus 25 degrees Celsius in here. It's not even minus 25 degrees Celsius out there, right? This is a really cold star. And we think this star is so cold it may have frozen water and stuff in its atmosphere. What a weird thing to call for a star that's below freezing, right? But that's what we're finding, all right? Because of these low temperatures, brown dwarfs probably have very similar atmospheres to exoplanets. The right side is the spectra of these brown dwarfs is sort of breaking up the light as a function of wavelength. And you can see when we do that for Saturn and we do this for one of the brown dwarfs, they look pretty similar because they have the same gases in their atmospheres. So we can study exoplanet atmospheres without actually looking at exoplanets by looking at these things. At these low temperatures, you can also get things that rain out of the atmosphere. So these is a list of all the minerals and even molten iron that condenses in the atmospheres of these objects. Think about that kind of weather. Molten iron rain. You thought it was bad today. All right, we don't got that. Now, for those of you who are capitalist-minded, corundum turns out to have different forms, including gems. So corundum with chromium impurities is rubies. Chromium with iron, titanium, and chromium impurities are sapphires. You can also paraparacha. So if anyone wants to go on a venture with me to mine some brown dwarf atmospheres, just talk to me afterwards. Now, brown dwarfs, so these look like planets, but they also could host planets themselves. I know that I think the last Astronomy on Tap, there was a talk on TRAPPIST-1. All right, this is a really exciting system still. It's 7 Earth-sized planets around a low-mass star. That star is so low mass, it's right up against the brown dwarf mass limit. Right? It's about 8% of the mass of the sun. Remember that brown dwarf limit is about 7% of the mass, so it's right up against it. And we don't think there's any reason why you couldn't form these kind of planets around lower mass things. And the meeting that Brett was talking about, where Didier found out he was getting this Nobel Prize, was a meeting to look for planets around brown dwarfs. All right? So this is how it all connects up. These are the kind of things that people are looking for. Now, if that's not enough, wait for it. maybe there's life in brown dwarfs. Ooh, okay. So this is a paper that was published. This was published earlier this year, back in May, by Avi. Okay, so some of us know who this is. All right. And the conclusion from the abstract is we show that the total habitable volume in the atmospheres of cool brown dwarfs is possibly larger by 2 orders of magnitude, 100 times, than that of Earth-like planets. Now we can debate on the complete insanity of this paper. However, it's intriguing, right? Maybe there is a way you can form life in these things. The other thing that's cool about brown dwarfs that I think is amazing is that every brown dwarf that ever formed still exists and will exist forever. Remember I talked about the lifetimes of stars. That lifetime is based on them fusing hydrogen and running out of that hydrogen and blowing up and dying. All right? These things don't fuse hydrogen. So they're the undead, right? They never die. So they can be around forever. I mean, they could merge with other stars, brown dwarfs, fall into black holes, stuff like that. But barring a disaster of that order, right, these things are going to be here when all of the other stars burn out and there's no more material left to form stars. These little guys are just going to be floating around by themselves. That's cool. Okay. All right. So those are all the cool things I have about brown dwarfs. I'm happy to take any questions, and thank you very much. Again.